Hello everyone. In last lecture we discussed about the definition of sensors, difference between the sensor and the transducer and why we need sensors. So in this lecture we will discuss about the definition of sensor technology and the definition of direct and complex sensors. So it is a technology that uses sensor to acquire information by detecting the physical, chemical or biological property or quantities and convert them into readable signal. So the technology by which we can acquire the information, that is physical information, chemical information or biological information. So by this we can say that uh, we want to measure pressure, temperature, heat, then we will acquire this information by using some sensors, and the technology that uses sensor to acquire this type of information which cannot easily measurable, and the sensor will acquire this information, and then sensor will convert them it into readable signal. Like temperature, we do not know what the temperature in our surrounding, so by sensor we can get the accurate value of the temperature around us. So in this way sensors are used to acquire some physical uh, quantities or properties or biological quantities or properties or chemical, and then they convert it to readable signal. The advantage of this is that some quantities which you can't measure, like heat, temperature, pressure, flow, so they can be easily measured by sensors. So by sensor, what we means, sensor is a converter of generally non-electrical effects into electrical signal. So it will convert non-electrical effects into electrical signal. That electrical signal, why, what is the advantage of electrical signal? Their signals can be channelized, modified, and they can be processed, and often several transformation steps are required before the electrical output signal can be generated. So in a sensor we may have different transducers present, and by that transducers several transformation can be done before that electrical output signal is generated. These steps involve change of type of energy. So the several transformation steps require change of many types of energy or physical property of materials, wherein the final step shall produce electrical signal of a desirable format. But in the final step you will always get electrical signal of a desirable format so that it can be used for display purpose. Generally there are two types of sensors. We already discussed these two types of sensors in previous lecture, direct and complex sensor. So by a direct sensor, it is one that can directly convert a non-electrical stimulus into electrical output signal. So by direct we can say that it is a direct converter of non-electrical quantity into electrical output signals. But many stimuli cannot be directly converted into electrical quantities, so there may be required for multiple conversion steps. So in this way we have two type of sensors, direct and complex. For example, if suppose one wants to detect displacement of an opaque object, so how we can measure the displacement of that object? A fiber optic sensor can be employed. So here we can use a fiber optic sensor, a pilot light beam, or that signal is also known as excitation signal. It is generated by the light emitting diode, and then this light flux enters the optical fiber, then propagates through it, then exits toward the object. So firstly we have a excitation signal that can be generated by LED, and that signal laser signal is entered into the optical fiber, then it will propagates and it will be go towards the object. Then after striking the object, it is reflected from its surface. The reflected photon again enters into the receiving optical fiber, propagates towards a photodiode. Now instead of LED we have a photodiode in receiving optical fiber, where it is detected to produce electrical current. What is a photodiode? Actually, the purpose of photodiode is when light will fall on photodiode, it will produce some electrical current that represents a distance from the fiber optic and to the objects. So in this way, we can measure displacement of an opaque object. Such a sensor involves transformation of electrical current into photons. So this sensor requires transformation of electrical current into the photons, then propagation of photon through some reflective media, that is the fiber, then reflection from the object, then propagation again through the fiber, then conversion of back it into the electric current. Therefore, such a sensing process includes two energy conversion steps and also a manipulation of light. So this type of sensor is also known as complex sensor because it requires many conversion step, and at the last step we have electrical quantities as a output. So there are several physical effects that results in direct generation of electrical signal. So in direct sensor, many physical effects can be used for direct generation of electrical signal in response to non-electrical influences, and these physical effects can be used in direct sensor. So examples of direct sensors are thermocouple, that is thermoelectric effect. It is also known as Seebeck effect, that uses temperature difference to generate voltage. Piezoelectric piezoelectric crystal, uh, that uses some pressure or force to be applied on piezoelectric material, and then that will generate a corresponding voltage across the piezoelectric crystals. Same a photo effect, as in photodiode we used some photons are uh, bombarded on any screen, any photodiode, and then it will generate some electric currents. Other conversions of energy that do not produce electrical output are performed by a device known as transducer. So as we discussed in previous lectures, the transducer is only a type of energy converter circuit. The physical effects that can be used to convert one type of energy or property into another non-electrical energy, they may be termed as transducers. We already know the difference between the transducer and the sensor. Now, electric charges, fields, and potential. We can sense these things. So, firstly, we know or we must know about the what are electric charges, what are fields, what are potentials. A well-known phenomena, the possibility of generation of sparks by friction involved in walking across the carpet. Sometimes when you will walk across a carpet, then it is possible only due to the friction, and there sometime you can see that some sparks. So these sparks, how these sparks occur, this is the result of the triboelectric effect, that it is a process of electric charge separation due to object movement. So in triboelectric effect, there is charge electric charge separation occurs due to friction or object movements of or air turbulence, atmospheric electricity, etc. So this type of sparks are generated by triboelectric effect. And why these sparks occur? Because of electric charge separation. There are two kind of charges, positive charge and negative charge, and like charges repel and unlike charges uh, they will attract each other. A triboelectric effect, it is a result of mechanical charge redistribution. So as I told you that triboelectric effect is the in this electric charge separation will occur. So it is a result of mechanical charge redistribution, means charge will be transferred from one body to another body. For instance, rubbing a glass rod with silk strips. So if we rub a glass rod with silk glass rod strips of electrons from the surface, silk strips of electrons from the surface of the rod, means silk will acquire electrons and it will get negative charge, while it will leaving abundance of positive charge, giving a rod a positive charge, means there is a charge separation will occur from some charge from the glass rod will be uh, goes to the silk. So in this way there is a separation of charge will occur, and this separation of charge is known as triboelectric effect. It should be noted that the electric charge is conserved. You know, electric charge is conserved always. It cannot neither be created nor be destroyed. Electric charges can be only moved from one place to another place. Like from glass rod, some electron move to the silk rod, leaving some positive charge on the glass rod. Giving negative charge means taking electron from one object and placing them onto another, charging it negatively. As in as in our example, silk rod acquires negative charge. The object which loses some amount of electrons is said to get a positive charge. So you can see the video for triboelectric effect in the link given in the PPT. So a triboelectric effect influences an extremely small number of electrons as compared with the total electronic charge in an object. So it always affects only a small number of electrons. So only small number of electrons will be transferred from one object to another object. But actual amount of charge in any object is very large. So to illustrate this, let us consider a total number of electrons in an old US copper penny. So suppose we have an old US copper penny and this coin weighs 3.1 gram, and it can shown be that the total number of atoms in it about 2.9 into 10 is to the power 22 atoms present in this copper penny. A copper atom has a positive nuclear charge of 4.6 into 10 is to the power minus 18 coulomb, and respectively the same electronic charge of the opposite polarity. So copper, because atom is electrically neutral, so it has positive charge of 4.6 into 10 is to the power minus 18 coulomb, and same electronic charge is also present in the atom. A combined charge of electron in a penny is Q is charge 4.6 into 10 is to the power minus 18 coulomb per atom, multiply with 2.9 into 10 is to the power 22 atoms. So net charge in the penny is 1.3 into 10 is to the power 5 coulomb. It is very large charge, as we know that 10 is to the power 5 is a bigger quantity. This electronic charge from a single copper penny may generate sufficient current of 0.91 ampere to operate 100-watt light bulb for 40 hours. So as we can see, this is large, copper penny has large amount of charge, and separation from of this charge may occur, and this can result in a current of 0.91 ampere 0.91 ampere to operate 100-watt light bulb for 40 hours. So with respect to electric charge, there are three kinds of materials. So by electric charge we can define three kinds of material: conductors, isolator, and semiconductors. So what are conductors? Electric charge are free to move through the material. In conducting material there are, you can get you can have a large number of electrons which are free to move through the material. Isolators, they are not, although there is no perfect isolator, but for practical purpose many materials are considered to as perfect isolator. So there is no free charge present in the material, then that material is known as isolator, but physically this is not possible. Then third type of materials which are very important for our subject is semiconductors. Semiconductors are intermediate between conductors and isolators in their ability to conduct electricity. So their conductivity lies between conductor and isolator, means they have some electrons to move through the, some electrons are free to move through the materials. So well known examples of semiconductors are silicon and germanium. For the sensing technology, semiconductors are very interesting materials. Why they are interesting material? Because their ability to conduct electricity, and these can be manipulated by applying external inputs like electric charge. So like electric charge and magnetic field and light. So electricity or to conduct conductivity can be changed by applying some electric charge, magnetic charge, and light. So for sensing purpose, suppose some electric changes are occurring in a nearby an object, and there is a sensor, and sensor will detect that changes. Then that sensor can produce sufficient electric output by detecting that change. So semiconductors are very important materials for sensing purpose. So we have a positive charge, test charge in vicinity of the charge object, and electric field of spherical object. So now we are defining what is electric field and what are electric potentials. Figure 1a shows an object which carries a positive electric charge Q. So this is a positive charge electric charge Q. If a small positive electric charge Q naught, you can see in between A and B figure there is small positive charge plus Q naught, and some force is exerted on that positive charge which is outward, and this small test charge Q naught is positioned in the equivalent of charge object. It will be subjected to a repelling electric force. Why repelling? Because like charges repel each other. If we place a negative charge on it or nearby it, it will attract the test charge. In a vector form, the repelling or attracting force is shown as small f. A fact that the test charge is subjected to force without a physical contact between charges means that the volume of space, that the surrounding volume around the charge is occupied by test charge may be characterized by a so-called electric field. So the field around this positive charge, where its effect can be felt by another charge, is known as electric field, and the direction of electric field is radial outward from the positive charge, which is shown in the B diagram of figure 1. The electric field in each point is defined through the force. So we can define the electric field force per unit test charge. That test charge can experiences when it is placed near another charge. So here E, capital E is a vector of the same direction as F, because Q naught is scalar. It is a scalar quantity. The field is induced in figure 1a by the field lines, which is in every point of space are tangent to the vector of force. So in figure 2 we have three figures A, B and C. So first is the electric field around an infinite line. It is always readily outward and tangent to the road. B is, we have infinite sheet, and from that infinite sheet it is also suppose that sheet have plus charge, so it also has outward electric field. And similarly pointed conductor concentrate electric field. C is the, we have a conductor then can concentrate electric field. So if this conductor has positive charge, then field is radially outward. Electric lines of force are radially outward, and if it is negative charge, then electric lines of force are inward. So by definition, the field lines start on the positive charge and end on the negative charge. The density of field lines indicates the magnitude of electric field E and any particular volume of space. Means if we have large number of electric lines, then we can say then electric field is very strong nearby that object. If electric charge is distributed along an infinite or for practical purpose long line to a, the electric field is directly perpendicular to the line. The electric field around the charged object can be described not only by the vector E. So electric field around that plus q charge is not only defined by that vector quantity E, but by a scalar quantity electric potential V as well. And you are engineering student, I hope you know about these terms. You studied in your previous semester electric potential, electric field. So this is just a revision. Both quantities are, both quantities means that electric field intensity E and vector scalar electric potential V are related, and usually it is a matter of convenience which one is to be used in practice. It depends upon the application. A potential, now we want to define a potential. It is rarely used as a description of an electric field in a specific point of space, but we maximum time defines potential difference, that is known as voltage between 2 points in the most common quantity. It is the most common quantity in the electric engineering practice. What it is known as voltage difference, means difference of 2 points. To find the voltage between two arbitrary points. So how we can define or derive the expression for electric potential? A small positive test charge q naught, if the electric charge is positioned in point A, it stays in equilibrium, being under influence of force q naught E. We are placing this q naught at a point A. Suppose we have this plus q naught charge at a point near the object, and A point is near the object and B point is far from the object. If the electric charge is positioned in point A, it stays in equilibrium, being under influence of force q naught E, and it may remain there theoretically infinite long. But now if we try to move it to another point B, we have to do some work against the electric field minus WAB, which is done against the field. So why a negative sign is there? Because we are doing some work against the electric field. To move the charge from A to B defines voltage between these 2 points. So VB minus VA is known as minus WAB into Q naught. For convenience, suppose this point A is chosen to be very far away from all charges at infinite distance. Then electric potential at that point is considered to be zero. So here VB minus VA becomes zero. So V will becomes minus W Q naught. This allows us to define electric potential at an other point, which is known as potential is equal to work done in carrying a unit positive charge Q naught from one point to another point.